So now we're going to take a look at some basics of electrical theory and electricity. The first thing we want to define here is what exactly is an electrical current or electricity. So we can think of this as just another form of energy. So electricity or electrical energy, just a different type of energy, but how it resolves is different than all the other forms of energy that we looked at previously. So electricity results from the movement of charged particles, and as we know, there are two charges that we're familiar with. We have positive charges, we have negative charges. When we talk about electricity, though, we're usually referring to negatively charged electrons, so the movement of electrons through some sort of a conductor, which is usually a wire. Copper wire, for example, metals are good conductors. That is usually what we are referring to. So that is what electricity is. Now, a couple things to note here when it comes uh, to the charges. So we mentioned positive charges, negative charges. We talked a lot about the atom and the subatomic particles earlier on in the semester. And as we recall from that discussion, there are two particles that are charged in a typical atom. Those would be the protons, which carry a positive charge. And then we also have the electrons that would carry negative charges, right? So protons are positively charged, electrons are negatively charged. So we're going to focus here on the movement of electrons because those are the subatomic particles that are much more easily lost in an atom than the protons. The protons are in the nucleus, remember, and they're kind of tethered to the rest of the atom, whereas the electrons are much more easily lost. Right, things lose, things gain electrons, share electrons. So we're going to look at the movement of electrons in our discussion of electricity. Now, an electron or anything with a charge we can quantify what that is. And specifically now the charge on an electron, on one electron is 1.60 times 10 to the negative 19. And then the unit here that we have for charge, the SI unit, is this uppercase C. That's called a coulomb. So it's a very, very small, an individual electron has a small charge, small negative charge, but there's a charge there nonetheless. And the fact that it's negative is really important. So that's the charge there in coulombs, which is the SI unit for charge. Now, what do we know about charges generally in terms of how they interact with each other? Well, intuitively, we know, and we also discussed this back in the earlier sections, we looked at the subatomic particles, is that if you have opposing or opposite charges, the opposite charges will attract each other. Okay, so positive attracts negative and then vice versa. And then we know that like charges will repel. So for example, two positive charges will repel each other. Two negative charges will repel each other as well. So that simple observation gives us those two observations give us some important perspective on what's known as the electrostatic force, which again is just the force of attraction between opposite charges or force of repulsion between like charges. So this can be summarized in a mathematical law. So mathematically, as you know, most laws can be represented by a simple math relationship. So mathematically, that electrostatic force can be represented by a law known as, believe it or not, Coulomb's law, named after the same person, Charles Coulomb, after which the unit of Coulomb was named. So Coulomb's law says that we were able to calculate the magnitude of that force F as being equal to some sort of a constant. So this is, we represent a constant by the symbol K. Constant means that that thing, whatever that is, doesn't change. Times the product of the charges that are involved. Okay, so these are two charges here. So the product of those two charges divided by the distance between them squared. So R here is the distance between those charges Q1 and Q2, whatever they happen to be. So mathematically, that force can be calculated. We can also make some general relationships based on the simple equation. So for example, we have the charges themselves that are in the numerator in this equation, right? So we're not going to worry about K here. Okay, K is a constant. This doesn't change. We're not going to worry about what that actually is. The fact that it doesn't change means that we can not ignore it, but we don't need to consider it when it comes to these types of relationships that we're going to draw. So if the charges are in the numerator, so if the magnitude or the size of the charge Q1 or Q2 increase, well, then the force, the magnitude of the force will increase as well, right? Because those two things are in the numerator. They're going to make the number, overall number here, bigger, right? So as +1 versus +2, well, the +2 being a bigger number will have a much larger force, twice as much as one that's like +1, for example. The other thing that we'll notice here is that the distance between the charges also comes into play. So that's in the denominator. So we can say then is if R, which is the distance between the charges, increases, okay, and that's in the denominator now. So now we're dividing these things on top by a much larger number on the bottom. Well, then what we'll see is that the force is going to decrease. Right, the electrostatic force of attraction will decrease. So for example, if I have a charge over here and a charge over on this side, right, there's a fairly big distance between them. Okay, so R there is fairly large. The denominator being large means the force of attraction here will be small. If I have those same charges that are a lot closer together, now the distance is less between them. So if the denominator decreases, right, then your force of attraction is going to increase. And that should make intuitive sense too. If you have two charges that are separated by a very, very big distance, they're not really going to see each other. They're not going to attract each other. Whereas if they're closer together, it's much more likely for them to be attracted to each other, right? So that's a way to interpret Coulomb's law, which just simply relates the force, the electrostatic force, to the magnitude of the charges and then also the distance between those charges.